ይስጥልኝ ተማሪዎች እንዲሁም ወላጆች ሰላምታዬ በያላችሁበት ይድረሳችሁ። እኔ መምህር ተፈራ እባላለሁ። እንግዲህ ከዚህ በፊት በነበረን ግንኙነት ላይ ወይም ዲስከስ እናደርግ በነበረን ቆይታ የ11ኛ ክፍል ዩኒት 5ን ወርክ ኢነርጂ ኤንድ ፓወር የሚለውን ሐሳብ ተነጋግረናል። ጥሩ ነጥቦችን እንዳገኛችሁ ተስፋ አድርጋለሁ። ስለዚህ ዛሬ ደግሞ የ11ኛ ክፍል ዩኒት 6 አንጉላር ሞሽን ወይም rotational motion የሚለውን ኮንሴፕት ለመነጋገር እንሞክራለን። So today we'll try to discuss about the concept of angular motion or rotational motion. So in this topic, after we accomplish or after the completion of this lesson, we should have to gain knowledge and understanding of rotational motion. We are able to define basic terms under rotational or angular motion. As well, we are able to state the law of conservation of angular momentum. And at last, we'll develop a skill or techniques of solving problems concerning on rotational motion. So, in this concept, first we should have to define what rotational motion mean. So, what do you mean by angular motion or rotational motion? Well, angular motion or rotational motion is a common motion which is found in our day-to-day activity, and it is defined as the rotation of a rigid body or rigid object about a given axis. So what does it mean by a rigid body? Here we have a term which is known to be rigid body. What do you mean by rigid body? You should have to define rigid body. Well, rigid body means it's a body, non-deformable body, in which the relative position between the particles of that body remains constant despite the change of motion. Therefore, rigid body is a body which is non-deformable, and the relative position between the particles remains constant, always remains constant. Therefore, the rotation of such bodies is known to be angular motion or rotational motion. Students, can you give me an example of rotational motion which is faced in your day-to-day life activity? Please. Well, there are several examples in our day-to-day activity that's face about or rotational motion. And the most common are the motion of a wheel of vehicles, car, bicycle, motorcycle, and so on. They tend to have a rotational motion, a wheel of vehicles. The other thing is whenever you open a door or a window, you face the same motion, angular motion or rotational motion. Planets revolve around the sun or around any star. They do have a rotational motion. Gears, we can consider gears, engines, and so on. They can be considered as rotational motion. Every electrical component in your home, they tend to have a rotational motion or angular motion. Ice skaters, usually in movies, you can see that ice skaters rotate or spin around their axis, so that we can consider it to be rotational motion. Therefore, the key point in describing rotational motion is the axis of rotation, the axis and radius. These are the two key points. For example, if you have something rotating bodies like this, you can consider this as an axis, and there might be a point of discussion here. Here is the particle that rotates about the axis. Therefore, the axis is through this, and the radius means always whenever you take radius is the distance between the point and the axis. That is it. That is what we call radius, r. Then, under rotational motion, or we can categorize rotational motion into 4, or the key features to study rotational motion is, first, we should have to discuss about rotational kinematics. kinematics. There is a kinematics part. I hope you have learned in Unit 3 about the concept of kinematics. Kinematics is a study of motion without the cause, without the force. And the other point is rotational dynamics. Dynamics studies about the motion and motion variables as well as the cause or the force. Therefore, we have rotational kinematics, we have rotational dynamics, we have rotational work, energy, and power, as well as we have rotational angular momentum. Therefore, these are the concepts I need to study or classify or categorize. Then, whenever we study about angular kinematics, there are key features or there are key terms that we should have to consider in rotational motion. And these key terms are, the first term is angular displacement. The terms that should be defined under kinematics or any concept in rotational motion are angular displacement, angular velocity, angular acceleration. We have also a translational or linear terms, linear velocity, linear acceleration or tangential acceleration. We have a centripetal acceleration. We have also a centripetal force. These are very, very important terms. Therefore, first let's try to see about angular displacement. What do you mean by angular displacement? I hope in the previous lesson you have learned about a linear or a translational motion. Whenever you take a linear motion, suppose here if you have an object, you can consider a box, for example. You can consider a box. If this box is translated here, at some point, if it reaches here, every point has a linear movement. Every particle on this object has a linear motion. So linear motion or translational motion, we can call it. But when we define rotational motion, there is an axis, and on that axis, there are particles trying to rotate about that axis. Therefore, we should have to discuss about these points. First, let's try to discuss about angular displacement. Students, I hope in your lower grade, you have tried to see about this term. I hope in grade 10, you have learned already this point. But now let's see, let's take a rotating object. Let's consider a rotational object here. Let's take the usual example, CD, which is a compact disk. Let's take a disk rotating about its fixed axis. Therefore, in this point, let's take a reference point here. We have a reference point here. At this point, at this line, we have a single point. Let's call it to be P. Here we have a point P on that CD or on that compact disk. Now, after a while, it tends to rotate and reach here. The point came, initially it was around here, now it reaches here. While this particle, let's call it point P, while this particle tends to rotate from this initial reference point P, from here, now it reaches here. While it moves an arc length S, it covers an arc length S. What do you mean by angular displacement then? Well, the point covers an arc length S, but at this axis, there it subtends an angle theta. It subtends or covers an angle theta. Therefore, mathematically, angular displacement can be defined as the ratio of the linear displacement S over radius r. We can call it r. We can define it as S over r. Therefore, here we have an arc length S over r. This is r, the radius r. We have already mentioned it, the distance between the point and the axis, r. Therefore, arc length, or we can call it to be a linear displacement or a translational displacement divided by the radius r gives us angular displacement. In this concept, the unit of angular displacement can be determined as the dimension of angular linear displacement over the dimension of radius r. To determine what? The dimension or the unit of angular displacement. Then here the dimension is cancelled out. Meter will be cancelled by meter. It is dimensionless, but it has unit, and that unit is known to be radian. Radian. We call it to be radian. In terms of radian, it's possible to substitute meter over meter, centimeter over centimeter, kilometer over kilometer. Therefore, it's possible to substitute it as meter over meter in terms of radian. So 1 rad, what do you mean by radian then? Well, what radian means, it is the angle subtended by equal arc lengths and radius. Here we have stated that we have an arc length S, and here we do have radius r. As this arc length is the same as that of the radius r, we have 1 rad. We call it to be 1 rad. Therefore, angular displacement here can be measured in revolution, in radian, and in degree. It's possible to measure it in revolution, rad, and degree, but the SI unit, or the standard unit, is considered to be radian. It's possible to measure it using revolution, degree, or rad. We can have, it's possible to change one into the other. And the other point is angular velocity. We have defined angular displacement. Mathematically, it is arc length or linear displacement over radius r. But now let's see about angular velocity. Well, angular velocity is the measure of speed or velocity of a given object, the rate of change of angular displacement. Therefore, angular displacement per unit time t gives us, okay, we can have angular velocity. And the SI unit of angular velocity is, the SI unit of angular displacement is rad, and time is second. So rad per second is SI unit of angular velocity. The other point is angular acceleration, and angular acceleration is defined as alpha. We'll use alpha. Whenever we define angular velocity, we use omega. Actually, omega, there is a capital omega like this. We are not going to use that. We have to use the smaller one, omega. Therefore, we use omega here. And angular acceleration is the rate of change of angular velocity. It can be defined as change in angular velocity. Here is delta W over delta T. This is angular velocity. The rate of change of angular velocity is known to be angular acceleration. And its unit is rad per second squared. This is not rad per second squared. This is SI unit of angular acceleration. Rad per second squared. Rad per second squared is a SI unit of angular acceleration. The SI unit of angular velocity is rad per second. The SI unit of angular displacement is rad. Now let's see about the translational or the linear quantities. So what are the linear quantities? Well, the linear quantities are the linear velocity, the linear acceleration. Therefore, to define what tangential velocity or a linear velocity mean, in linear motion or in a lower grade or in kinematics concept, you have defined that velocity v is change in displacement over change in time t. Change in displacement over change in time t. And displacement can be given as s is equals to r times theta. Previously, here we have states that theta is equals to s over r. From this, when you crisscross, s is equals to r times theta. Then, if you have s is equals to r times theta, to determine the change in arc length, whenever there is a change in arc length, for example, if this particle moves from this to this, we have the initial arc length, and again, when it reaches here, we have another arc length. Therefore, the change in arc length appears as, it's not due to the change of radius. The radius remains constant. Whenever this particle reaches here, here, everywhere, the radius remains constant. But one thing changes, and the angle changes. When the particle reaches here, the angle changes. When the particle reaches here, the angle again changes. Therefore, the arc length, whenever there is a change in arc length, or call it a linear displacement, the radius remains constant, but there will be a change of angular displacement. Therefore, when you take the ratio of these in terms of arc lengths, when you substitute as r times the arc lengths, we can have such an expression. The angular displacement over change in time t gives us omega, which is angular velocity. Therefore, linear velocity can be defined as r times omega. Well, this is how we define tangential velocity. Tangential velocity or linear velocity can be correlated with angular velocity in terms of the radius r. Previously, we have said that angular displacement is linear displacement over radius r. And now, the angular velocity can be defined as linear velocity over r. Okay, the angular velocity is defined as linear velocity over radius r. Angular displacement is defined as linear displacement, or we call it as arc length over radius r. So the other point is we have to define what tangential acceleration or a linear acceleration is. So sometimes it's possible to use it A or AT as a subscribe. It is the velocity which is acting along the tangent, and it is defined as, since we have learned in linear motion, acceleration is defined as the rate of change of linear velocity. Therefore, acceleration is change of velocity. We have already defined velocity v as r times the angular velocity. This is the tangential velocity. This is the angular velocity. Therefore, here the tangential acceleration is defined as the change of tangential or a linear velocity over change in t. Therefore, whenever there is a change of linear velocity, if there is a change of velocity, it's not due to the radius. We can keep the radius r for perfect circular motion. We can consider r to be constant. The change appears due to the change of what? The change of angular velocity. Therefore, we can substitute it here. The change of angular velocity, in terms of change of angular velocity, we can substitute here. Therefore, r times change in omega over change in t. We have already defined that the angular velocity over change in t gives us angular acceleration alpha. Therefore, tangential acceleration is equals to radius r. We can interchangeably use this as a small r or capital R. Usually we use small r actually here. Therefore, A is the linear acceleration or the tangential acceleration, r is the radius, and alpha is the angular acceleration. So previously we have stated that angular displacement can be defined as linear displacement over radius r. This is how they correlate, the linear and angular parameters. And we have defined angular velocity as the linear velocity over radius r. And now the angular acceleration can be defined as the linear acceleration or the tangential acceleration over radius r. So here, angular displacement, angular velocity, angular acceleration. And they can be correlated in terms of radius as s over r, v over r, a over r. S is angular linear displacement, v is linear velocity, and a is a linear or tangential acceleration. Now let's see the other acceleration, which is known to be centripetal acceleration, or known to be radial acceleration, or sometimes known as normal acceleration. It is the acceleration which is always acting towards the center, Here you have a circular point. Suppose here you have a particle. This particle might rotate about this axis. Therefore, there is an acceleration which is acting towards the center. That acceleration appears due to the change of velocity. Look at here. The change of velocity, not in magnitude, but in direction. For example, if this particle initially moving with 10 meter per second, let's consider it to be 10 meter per second, 10 meter per second. For example, let's take the magnitude to be 10 meter per second. In this case, it's moving upward to the north. Let's be moving here. When it reaches here, the magnitude remains constant, 10 meter per second. The magnitude remains constant. But one thing changes, the direction. The direction changes. Therefore, velocity is a vector quantity. Therefore, whenever there is a change of direction, the velocity changes due to the direction, not in magnitude. Therefore, due to the change of direction of a velocity, there is an acceleration which is acting towards the center. And that acceleration is known as centripetal acceleration. Centripetal acceleration is acceleration which is produced due to the change of velocity in direction, not in magnitude. The magnitude remains constant. Therefore, centripetal acceleration can be mathematically given as velocity v squared. Which velocity? The linear velocity. This is linear velocity or tangential velocity v squared over r. Previously, we have defined the linear velocity as r times omega. R times omega. What do you mean by r times omega? Well, omega is the angular velocity, v is the linear velocity. Whenever you substitute here, we can resubstitute as centripetal acceleration is equal to r times omega the whole squared over r. Okay, so when you cancel the 1r, we can have centripetal acceleration as r times omega squared. Omega squared. So it's possible to have such an expression. Centripetal acceleration, or call it radial acceleration or normal acceleration, is equals to the tangential velocity squared over r. Or it's also possible to express it in terms of angular velocity as r times omega squared. And the other point is a force. Force appears due to acceleration. Actually, net force is equals to mass times acceleration. You have learned it under the concept of dynamics. Therefore, centripetal force is a force which is always acted towards the center, and that force appears due to the centripetal acceleration. We have defined that centripetal acceleration or radial acceleration is always acting towards the center. Due to that acceleration, we have also a force, and that force is known as centripetal force. The force which is acting towards the center is known as centripetal force. So generally, net force is equals to mass times acceleration. This is the basic law of dynamics, or Newton's second law of motion. Call it to be law of acceleration. We can have mass times acceleration. Therefore, this acceleration, centripetal acceleration, the force is also known to be centripetal force, a force which is acting towards the center. Therefore, it can be resubstituted as m times the linear velocity squared over r. It's possible to use this, or it's also possible to use angular variables. We have defined centripetal acceleration as r times omega squared. Previously, we have defined it like this. Therefore, we can substitute as mass times, instead of centripetal acceleration, we can have r times omega squared. We can have such an expression for centripetal acceleration. Let's proceed again. Now let me ask you one question. So far we have tried to see the different terms or quantities. What is the direction of angular velocity? Where is the direction of the angular velocity and angular acceleration? How do we determine the direction of such quantities? Actually, the tangential velocity, the tangential acceleration is somehow clear. But what do you mean by angular velocity? What is the direction of angular velocity? What is the direction of angular acceleration? And so on. So therefore, the direction of angular velocity and angular acceleration are always along the axis of rotation. They are always acting along the direction of the axis of rotation. That's it. Whenever there is a rotating object, previously we have mentioned different types of angular motion. Whenever there is a motion, angular motion, there is an axis and radius. Therefore, the angular velocity and angular acceleration are always acting along the axis of rotation. For example, here we have a CD or a disc or a wheel. It might rotate like this. From the view, we can possibly view from the top. It might be counterclockwise like this. Whenever we move and try to see from above, we have such a rotation. We can see it like this. Whenever it rotates like this, it is acting toward us as anticlockwise. Therefore, whenever it rotates like this, anticlockwise, we have a direction along the axis. This is the axis of the rotation, and along that axis of rotation, the direction of omega is represented like this. Therefore, it's so clear to observe it from this. when it rotates counterclockwise or anti-clockwise, you can grasp your hand around this. So the angular velocity is along the direction of the axis. Whenever it rotates clockwise, like this, you should have to grasp it, and your thumb points to the direction of angular velocity. Therefore, this is the direction of angular velocity. You can use right hand rule, or it's possible to use screw rule. Whenever you twist screw clockwise, it's moving downward. Or whenever you open and close a tab, okay? Therefore, whenever you twist it clockwise, it's moving into, that is the direction of angular velocity. Whenever you open, or whenever you turn it counterclockwise or anti-clockwise, it's moving towards you. Therefore, it's possible to use right-hand rule or screw rule to identify the direction of angular velocity and angular acceleration. And angular acceleration are acting along the axis, but sometimes similar to that of angular velocity or opposite to that of angular velocity. For example, for a faster moving object, for example, let's take an object which is rotating counterclockwise. It's rotating counterclockwise. So when it's moving counterclockwise, when you use right-hand rule, the angular velocity is acting along the axis of rotation. It's upward in this direction. That is the angular velocity. What is the direction of angular acceleration? Well, for a fast-moving object, for example, the object is moving counterclockwise, and it's moving faster and faster. Whenever the object is moving faster, the angular velocity and the angular acceleration are acting along the same direction, When we have a slow moving direction, for example, a given object might move slowly, gradually. Fast moving object is moving now slowly. Then if it moves gradually, decrease its velocity, the angular velocity and the angular acceleration are opposites. Therefore, for a counterclockwise moving object, let it be like this. Whenever you use right-hand rule, the direction of angular velocity is like this, in this direction. How about the direction of angular acceleration? Well, this object is moving gradually slower. It's not moving faster. Therefore, while it's gradually decrease, its angular acceleration opposes the direction of angular velocity. So this is the direction of angular acceleration alpha. Alpha is opposite to that of what? Angular velocity for a slower moving object, but for a faster moving object, the direction of angular velocity and angular acceleration are the same. Let's proceed. Let's summarize all the points now. Here we have defined angular displacement as S over R. We have defined alpha as the rate of change of angular velocity. Centripetal acceleration as the tangential velocity squared over radius r. We have also defined angular velocity as the rate of change of angular displacement, or it's also possible to correlate with the linear velocity as v over r, tangential velocity over radius r. And it's possible to crisscross this, and linear velocity can be defined as radius r times angular velocity. And again, for alpha or angular acceleration, tangential acceleration or a linear acceleration over radius r. Here we have, it's possible to crisscross. A linear acceleration or a tangential acceleration is given as radius r times angular acceleration. Centripetal acceleration can be defined as tangential velocity squared over radius r. It's also possible to correlate using angular velocity as angular velocity squared times r. And we have also defined the centripetal force as mv squared over r. So at this point, we could have a total acceleration, which is equals to the root of centripetal acceleration and tangential acceleration. Let's take here. For example, you could have such a rotating object. For example, here we have a tangential acceleration A. Let's call it to be tangential A. Just call it as A. Let's take circular path. Here you have a tangential acceleration. And the other acceleration acting we have discussed is the centripetal acceleration, AC, which is acting towards the center. What do you mean by total acceleration? Here you have total acceleration. Okay, total acceleration. This total acceleration is always found between the two accelerations, the tangential acceleration and the centripetal acceleration. And it's acting somewhere in between. This is known as total acceleration. And total acceleration can be mathematically given as centripetal acceleration squared plus the tangential acceleration squared under roots is given as the total acceleration. So these are the points previously discussed. Let's proceed. In translational motion, or in a linear motion, we can categorize motion depending on acceleration into three. One, uniform motion. Uniform motion is a motion with zero acceleration. The other point is uniformly accelerating motion. Uniformly accelerating motion is a motion with constant acceleration. And the other point is accelerating motion. Accelerating motion is a motion in which its acceleration varies or depends with time and position as well. Therefore, we can categorize it using acceleration. In this unit or in this topic, we just only focus on rotating bodies with a uniform acceleration or a constant angular acceleration. Uniformly angular acceleration. We are trying to see about motion of rotating objects with constant acceleration. Now let's take a point. For example, let's take a compact CD. In this concept, the angular velocity, angular displacement, and angular acceleration of every point, a rotating object, remains constant. For example, let's take a CD here. We have different points on this CD. Let's consider 3 points. Here you have point A, we have point B, we have point C. All these points are found on this compact disk. Therefore, if this compact disk is rotating and reach somewhere here, this point A might be transferred here. A, let's call it to be A. And this point might be transmitted and transferred here, point B, and C might reach here, C. Therefore, every point on this rotating object has the same angular displacement, the same angular velocity, and the same angular acceleration. Therefore, on a rotating object, every particle has the same angular displacement, angular velocity, and angular acceleration. But the other variables like tangential velocity might be changed. For example, for point A and for point B, we could have a different tangential velocity because tangential velocity depends on radius here. Therefore, from the axis point A, we have radius r. From the axis at point B, we have different r. For point C, we do have a different r. For different r, we could have a different tangential velocity. Therefore, for a rotating object, every particle has the same angular velocity, angular acceleration, and angular displacement, but we could have a different tangential velocities or tangential acceleration. Therefore, depending on the motion, we have already defined that for a uniformly accelerating motion, we have different equations. Therefore, from a linear motion, these are the well-known equations. For average and instantaneous velocity, we have average and instantaneous velocity, and for angular velocity, and we can have average and instantaneous angular acceleration. Therefore, these points we'll try to discuss it on our next session. So for today, it's all that I got. Bye-bye.